Prevalence is the total number of cases in a given population at some time divided by the total number at risk in that population at the same time. Now, the population at risk includes only people who could be afflicted by the disease. For example, if you're trying to quantify the prevalence of endometriosis in a community, only women would be included in the population at risk, since men are not at risk for uterine diseases. The total number of cases includes both old as well as new cases. And remember that prevalence describes a single point in time. Now, the incidence of a disease is defined as the number of new cases in some given period of time divided by the total population at risk during that same period of time. Thus, incidence describes new cases that occur in a time period, while prevalence describes all the cases at some given time point. Also, when calculating incidence, people who are not at risk for acquiring the disease, just as in prevalence, are omitted. However, this also includes people currently with the disease as well as people previously with the disease for conditions that cannot be acquired multiple times. So roughly speaking, the prevalence is approximately equal to the incidence times the disease duration. Thus, for chronic diseases like diabetes, the prevalence will be greater than the incidence because there are a larger number of existing cases. While for acute diseases like the common cold, prevalence is approximately equal to incidence because almost all of the cases are, by definition, new cases. Now, we talked a little bit about disease risk when we discussed incidence versus prevalence. Now let's begin by talking about risk by looking at the odds ratio. Do you remember what type of study uses the odds ratio? The answer there was case control studies. So the odds ratio is formally defined as the odds of exposure to some risk factor in a disease group over the odds of exposure to the same risk factor in a non-disease group. More simply put, does an exposure increase the odds that you have the disease, and how strongly is that exposure associated with the disease? In statistical terms, it means that the exposure is more associated with the disease than by chance alone. So looking at this 2x2 table, we can easily compute the odds ratio in 3 steps, and this can easily become 1 step with some memorization. So first, we need to determine the odds that an individual has the disease given that he or she has experienced an exposure. This is given by A, people with both the disease and exposure, divided by B, people with exposure who are healthy. Secondly, we need to figure out the odds of developing the disease without an exposure, or C, the number of people who got the disease without being exposed, divided by D, the number of disease-free, exposure-free individuals. Okay, now to compare these two groups and quantify the odds ratio, you simply divide this step by this step. Or in other words, A over B divided by C over D. And with some simple mathematics, the expression becomes A times D over B times C. Now, if remembering the derivation helps you, then you should go through the steps. Otherwise, you can cut to the chase by just memorizing this equation for odds ratio. Now, does an odds ratio imply causation? No, absolutely not. Only a correlation. There could be a third variable, some confounder that causes both the exposure as well as the disease, so don't be fooled. Now, the odds ratio is approximately equal to relative risk if the prevalence of the disease is not too high, but is not exactly the same. Okay, so here's a quick flash quiz. What type of study uses relative risk as a measure of association? That's right, the answer is cohort studies. The relative risk is formally defined as the relative probability of getting a disease in the exposed group compared to the unexposed group. It is calculated as the fraction of people with disease in the exposed group divided by the fraction of people with disease in the unexposed group. From the table, we can figure that the relative risk is calculated as A, all the people with the disease and risk factor, over A plus B, all the people with a risk factor in general, divided by C, people with disease but no risk factor, over C plus D, all of the people with no risk factor. Relative risk reduction is directly related to relative risk. It's the proportion of risk reduction that is attributable to the intervention as compared with some control. Relative risk reduction equals 1 minus the relative risk. For example, if you're on the Titanic and you're giving out life jackets, if 20% of passengers who have life jackets drown, whereas 80% of passengers without life jackets drown, then the relative risk would be 20 over 80, which is 0.25. Now, using that, we could calculate the relative risk reduction of wearing a life jacket, and that would just be 1 minus 0.25, which equals 0.75. So the relative risk reduction of drowning with a life vest is 0.75. So now let's discuss some other important parameters used for quantifying risk. The attributable risk is the difference in risk between the exposed and the unexposed group. That is, how much more risk does a certain exposure or factor confer for the patient. For example, if a patient jumps off one stair or jumps off a flight of 13 stairs, how much more will the extra 12 stairs contribute to the risk of a sprained ankle? The attributable risk is calculated as A, people with the risk factor or the exposure and the disease, over A plus B, everyone with a risk factor, minus C, people with the disease but no risk factor or exposure, over C plus D, everyone that has no risk factor or exposure. For example, we can see that if the probability of getting pneumonia as a smoker equals 2/3, while the probability of getting pneumonia as a non-smoker equals 1/3, we could conclude that the proportion of pneumonia occurrences attributable to smoking would be 2/3 minus 1/3, which of course equals 1/3. The absolute risk reduction is the decrease in risk associated with an experimental treatment as compared to a placebo or control treatment. The attributable risk and absolute risk reduction are important because they are used to calculate the number needed to treat and the number needed to harm. The number needed to treat can be calculated as 1 over attributable risk reduction, whereas the number needed to harm can be calculated as 1 over attributable risk. The number needed to treat and number needed to harm are commonly tested principles on the exam. You can think of the number needed to treat as the number of people who you would need to give some sort of treatment to prevent one person from getting the disease of interest. In contrast, the number needed to harm is the number of people you would need to expose to a risk factor in order to cause one person to acquire the disease of interest. Okay, that's a lot of information. Make sure you're familiar with all of the items that you see on this slide. Review the video, memorize the relevant equations, and you should be fine on test day.